Hi, and welcome to a flipped lesson for Algebra 2. This is a review for a quiz on basics about power functions, how they operate, what a power function is, how to tell if a function by an odd or even power, which direction the end behavior will be according to the lead coefficient. And it's basically encompassing everything that we learned in lessons 1 through 4. Okay, so let's start off with our basic definition of a power function. A power function is any function of the form y equals ax to the b. Okay, so notice there's no plus something or minus anything else. It is just the lead coefficient a multiplied by the variable x raised to the b power. And the only requirement is that a does not equal 0 and b does not equal 0. So if you have something like 5x cubed, that's a power function. 5 is your variable a, and this is b, so it's a cubic function, and cubic functions, they start low and, start low and turn and end upward. Okay, so a cubic function, and it's pulled 5 times, so this whole thing would be stretched by a multiple of 5. Okay, another power function would be anything with, say y equals 3 over x to the second power. I can rewrite this, and I can bring the x to the numerator and make it negative in the numerator, and that's still a power function. I can also have a power function where I've got a value of a square root, say, in the denominator. So I can have 5 square roots of x, and I can rewrite the square root of x as x to the 1/2, and then bring it to the numerator, and it would be 5 to the negative, 5x to the negative 1/2 power. Okay, so these are all examples of power functions. Something that is not a power function is if I were to take, say, 5 and multiply by x minus 1 and then square that would not be a power function. Okay, so when I would take the variable, the binomial x minus 1 and square it, I'm going to end up with lots of other terms. I'm going to end up with a trinomial, and then distribute the 5 in, and once I have other terms, not just a monomial term, then I don't have a power function anymore. Okay, so that's what a power function is. Okay, so the next thing you have to do is to be able to manipulate algebraically variables in the denominator and to reciprocate and bring them up to the numerator. So we saw a little example of that in the example that I used for the power function. Let me just use, say, the 4th power of x. So we have to be comfortable manipulating that and bringing the x to the numerator, making it negative, and raising it to the 1/4 power. So it's power over root. The power is understood to be 1 over 4. If I made that x squared, then it would be 2/4, and then I would reduce it to negative 1/2. If I made it x cubed, then it would be negative 3/4 as the power, and I would leave it that way. So manipulating in this regard is a skill that you need to know how to do. Okay, so the next topic would be on if a point lies on a graph with an odd exponent, how would you find out other points that also lie on the graph? Okay, so the concept of odd versus even exponents, and recalling that if you have an odd exponent for f at x for the function, then the y value will negate when the x value also negates. Okay, so let's take the point for -9, for instance. If this is a point on the graph, what would be also a point on the graph? So if I was to negate the x value, then the y value would also negate, and I would get -4, 9 as the answer there. Okay, now an even power means that if I have a value of y for a specific x, when I make that x negative, it will not change the value of y, and that's an even function. So again, let's use the same point. If I have the point 4, -9 on the graph, then changing the x value will not change my y value, and it would stay the same. Okay, so see the difference. Changing the x value negates the y value. Changing the x value keeps the y value. So even it keeps it, odd it changes it. Okay, and that's the notation that you should know. Okay, next. Zeros of a polynomial function. So if I have zeros of a polynomial function and I give them as -3, 4, and 6, okay, and I tell you that these are the zeros, how could I write the polynomial function? Okay, now there's going to be lots of different functions that fulfill these 3 zeros. In order to specify or be specific about one in particular, we would have to say that the graph also goes through a particular point. We would have to name that point, give that point. So this is just a general, how would you write that function? Well, if these are the zeros, these are the x equal values. So if these are the x equal values, x equals -3, +4, and x equals 6, you turn them into factors by adding the 3 to the other side and making this equal 0. So x plus 3, subtract 4, x minus 4, subtract 6, x minus 6. Okay? And if I want to just write a function, I need to know what a is. So any a at this point would be a function where these would be the zeros. Any a except, of course, a equals 0. So any a value would make that equal a polynomial function with those particular zeros. So you can virtually put in anything there. I could let a equal 2. There you go. There's a polynomial function with those zeros. I can let a equal -1/2. There's a polynomial function with those zeros. You could basically change it any way you want. You can just let it a equal 1, and there's a polynomial with those zeros, okay? Now, if we want to specify, if I want to know what's a polynomial with those zeros that go through a particular point, then that would require me to substitute that x, y point in, and then solve for that a value there. Okay. All right, the next one is determining whether or not something is an identity. So an identity is anything that equals the other side. It's an algebraic manipulation to make an equivalent statement. So if I want to determine if something is an identity, it's kind of like, let's just use the very simple example of the distributive property. If I have 4 and I'm going to multiply by 3x plus 5, and rewrite that equation, I would distribute the 4 in and get 12x plus 20. This is basically an identity. One side equals the other for all values of x. So it's an algebraic manipulation to rewrite it as an equivalent statement, equivalent algebraic statement. So that would constitute an identity. If I had something like x plus 1 and asked you, is that an identity? No, it's not an identity because those are not equal to each other. So an identity, one side would have to be equal to the other side. And generally to do this, you want to algebraically manipulate only one side of the equation in order to see if it's an identity. Okay, so I'm going to just use this one as an example of how to algebraically manipulate something. Okay, so if I want to see whether or not this is an identity, I would need to change one side of the equation to try to make it look like the other side of the equation. So in this case, I'm looking at the right and I'm thinking, well, if I make a common denominator here, I can rewrite it as a rational expression, like something like that. So let me try to do that. So this is a denominator of 4. 1 in disguise is 4 over 4, and that would be plus x over 4. 4 plus x, whoops, straighten that plus out. 4 plus x over 4 does not equal x over x plus 4. These are different, and so this is not an identity. Not an identity. Okay, so certain things will be, certain things will not be. They are not equal to one another. Okay, so sometimes we're asked to find which one's not, and sometimes we're asked to find which one is, and you have to be able to identify one side, manipulate it, and try to make it look like the other side to see if it's an identity. Okay, so let's practice doing that. We're going to see if the following equation is an identity. And this is x minus y multiplied by x squared plus xy plus y squared. And I want to see if it's an identity with x cubed minus y cubed. Okay, so the rule is I kind of like build a wall here, and I'm not allowed to cross the wall, meaning I can't add and subtract the two sides of the equation. I have to just manipulate this side and try to make it look like this side, okay? So I'm going to distribute the x minus y into this expression by x multiplying by everything, x cubed plus x squared y plus xy squared. Okay, so the x distributed into each of the three terms. X times x squared, x cubed, x times xy, x squared y, x times y squared, xy squared. I'm going to do the same with the negative y. So that's going to become a negative x squared y minus xy squared minus y cubed. Okay, now I'm going to try to see if there's any like terms that I can group together. So I have an x squared y here and an x squared y here. One's positive, one's negative. That's good because they'll cancel. So they cancel out. And then I have a xy squared here with a minus xy squared here. Again, that'll cancel out. And the only thing that remains now is x cubed minus y cubed. And it does, in fact, equal x squared minus y cubed. And so we say, yes, it's an identity. Okay? Notice we didn't touch the right side. We left it, and we just tried to transform the left to make it look like the right. And that's how you prove an identity. Okay. Next will be a question on, given a graph, to be able to write its equation in standard form. Okay, so given that the x-intercepts of a function and what they are, and then write the standard form of the equation based on it. Okay, so the graph of the function is going to look like something like this. Like that. Okay, and I'm going to put a point there and tell you that that's -4 and that's 7. Okay, so based on this polynomial function, a couple of things we know about it. So the end behavior are in opposites. So remember, opposites are odd. Opposite ends, odd. So this is an odd function. Okay, so there's going to be an odd exponent on the lead coefficient, the lead term. Also, there are 3 distinct zeros, so there's no turning point, there's no double root in this case. We have 3 distinct zeros. So let's just write down what they are first. They're x equals 4, x equals 0, and x equals 7. And then the next step is to turn these into factors. So the factors for this one is x plus 4. Now an x equals 0 factor, if I were to take x and minus 0, it would just be x. So x is a factor, and this one subtracts 7, it's x minus 7. Okay, so these are our three factors of our polynomial function. And we are going to write the equation for it. So we're going to take those three factors. Let me put my x out in front. There's one factor, there's two factors, there's three factors. And now I'm basically going to just double distribute my binomials and then distribute the x in and do that at the end. It'll be easier. So y equals x multiplied by x times x squared, negative 7x and 4x give me a combination of negative 3x and minus 28. Let's clean that up. So y equals x times x squared minus 3x minus 28. And now distributing that x in, it's x cubed minus 3x squared minus 28x. That's it, voila. This is your polynomial function that represents this graph and has those roots. Okay, now we're gonna create one where we're given a point and we're going to determine the polynomial function that is very particular to that one exact graph. Okay, so the question is this. Write an equation of a cubic function that has x-intercepts that are negative 4, negative 1, and 3. And it's going to pass through the point 140. So the polynomial function is going to pass through 140, okay? So that's going to be my x and my y. And then I'm going to set this into the a times your factors. Now there's three distinct roots or zeros of the function. I'm going to turn them now into factors. So this one becomes x plus 4, this one is x plus 1, and this one is x minus 3. And now I have the point 140. So 40 equals a 1 plus 4, 1 plus 1, 1 plus minus 3. So it's a times 5 times 2 times negative 2. 40 equals, that's 10 times another negative 2 is negative 20. So equals negative 20a, and dividing by a negative 20, negative 2 equals a. So the final polynomial function is y equals negative 2, x plus 4, x plus 1 times x minus 3. And the final thing it said is, if it said to put it into standard form, and this one doesn't, but if it said to put it into standard form, you would then take that end result, multiply these two together. So let's just do that really quick. I'm going to grab these two first. So that would equal x squared. 4x and 1x make 5x. Plus 4 times 1, which is 4. Oh, I had a negative 2 out there, so let me just squeeze that in. And I'm going to multiply that by x minus 3. And then in the last step, I'm going to distribute the negative 2 in. So x times all of this, and then negative 3 times all of this. So x times x squared plus 5x plus 4 minus 3 times x squared plus 5x plus 4. And that whole thing is going to times by negative 2. So there's my x minus 3 times the trinomial. That becomes x cubed plus 5x squared plus 4x minus 3x squared minus 15x minus 12, negative 2 times all of that. But let's clean it up first if we can. These are like terms, and these are like terms. So I'm going to simplify this a bit. So y equals -2 parentheses x cubed 5x squared minus 3x squared equals 2x squared. 4x minus 15x is -11x minus 12. And now bring in the -2. So -2x cubed minus 4x squared plus 22x plus 24. And that equals y, which equals the original factored form. This is in standard form, and this is in this one, which is the same, is in factored form. Okay, that concludes our review for your quiz, and study those questions and those concepts, and you'll be fine. See you tomorrow.